Today we are going to discuss something about tungsten inert gas welding process, also known as gas tungsten arc welding process, which is a very high quality welding process. This process is very important for the industry because it covers a varied nature of industries such as aerospace, nuclear, power plant, chemical plants and such applications, and thicknesses ranging from 0.5 to 500 millimeter. Now we will discuss in this session about the various features of the process, the advantages, limitations and its application. So today we are going to discuss about TIG welding process. TIG welding is a process where welding is done by the coalescence of two metals due to the heat from the arc between a non-consumable tungsten electrode and the base material. If required, shield filler wire is also added, and the entire assembly is shielded from the atmospheric oxidation by a shielding gas which is inert in nature, and usually argon or helium or a mixture of these two. Now the addition of filler material is based on the requirement, based on the job thickness and the specific property requirements. Now here in the slide you see the basic feature of the TIG welding process. The arc is between a non-consumable tungsten electrode, as you can see in the screen, between the tungsten electrode and the base material, and as you can see, medium of shielding gas, that is argon or helium, is surrounding the tungsten electrode and shields the arc, the molten pool and hot metal and any extra filler material that is added. Now once the sufficient amount of welding is created in that particular location, the starch starts moving, covering the entire length of the joint. Now as you can see in the picture, you can see the torch is connected to a power supply where the electric power is given inside along with the shielding gas. The filler material is added externally by using either manual method or by the automatic method using a mechanized wire feeder, as we can see later. To see the total welding setup, as you can see, the welding system actually consists of a welding power source which gives the electrical energy for the arc. That's the most important part of the system. The second important part is the torch which is connected to the power supply and then which holds the tungsten electrode, provides the shielding for the welding area, and then you have a gas system which is a gas cylinder plus a regulator plus a flow meter which feeds the required amount of shielding gas into the torch. Now all these things are connected in a single system for automatic welding as a total integrated controls. In addition, you have a foot switch which enables the welder to switch on and switch off the welding as required. Now what are the characteristics of this TIG welding process? The first and the foremost aspect which comes to our mind when we talk about TIG welding is the very high quality which can be achieved by this process, since it uses an inert gas and which will not allow any other chemical reaction to take place or any inclusion of any flux or slag into the system. This gives a very high quality as well as the highest strength possible for this. And the addition of filler material is extra, which enables even very thin sheet of welding to be joined. And this leads to another important aspect. Since the quality of the welding is very high, we also find that productivity is very low due to the low heat input, and requires a very high welder skill for achieving a high quality of welding. It can weld almost all metals. It can weld several dissimilar material combinations, several dissimilar thicknesses, as well as very thin sheet materials, even up to the level of 0.5 millimeter of stainless steel. Since the quality of the welding is of the highest order, this process is very widely used in aerospace industries and nuclear industries, where the cost is not an important factor, but the quality is very, very important. The second important application of this particular process is the food handling equipments such as beer cans, milk machines, or any component which comes into contact with food materials. The main advantage of this TIG welding process is that there is no biological formation of bacteria and all that because of the high quality of the welding achieved here. In other industries, the major application is For root pass welding of tubes and pipes in refineries or petrochemical industries or process plants, where the high quality is used for root pass welding and followed by the other processes like SMAW and MIG welding for improved productivity. And where there is a dissimilar thickness welding, also this is finding a very wide application. Thicknesses ranging from, for example, you can join 1 millimeter thick of tube to 100 millimeter thick of tube sheet in heat exchangers are very common using this particular process. Dissimilar material combinations like carbon steel to stainless steel welding can also be done, which is very difficult with other welding processes due to the high difference in the thermal conductivity and heat capacity of these materials. So these last two dissimilar combinations are basically use pulse TIG welding process for achieving the required quality. Now let's see the important various features of TIG welding equipment which contribute to this particular high quality and very good process. The first is the power source which gives the electrical energy to the system. The second one is the torch which holds the tungsten electrode and affects the welding really. The third one is a shielding gas system which gives a shielding requirement for the arc. Lastly, the filler wire addition which enables the welding to be completed according to the thickness requirement. And controls and accessories are added according to the requirement, which could be a simple thing as a high frequency start system or a gas flow system or water cooling system, or it could be even that of a filler wire addition through a wire feeder, automatic voltage control, or it could be a sequential programming system for the entire operation. Now let's see one by one the important parts of the system here. The power source is the heart of the total system which gives energy to the welding. As you may be aware, we have two types of power sources. One is a constant current type, the other is a constant voltage type. In this process, we are using constant current type of power sources where the current levels are almost constant throughout the welding even when there is a slight variation in the arc length. And this particular system can use either a direct current, that is DC, or alternating current AC, and both are employed in the case of TIG welding process. In DC, the electrode negative is connected, widely used in welding of steels, any amount of alloy steels, stainless steels, carbon steels, nickel alloys, copper alloys, titanium alloys, etc. The other type of welding, which is DC electrode positive, is not used in the industry due to the very poor efficiency obtained in this particular process. The second type of electrical power supply which is used is the alternating current power supply, which is used in aluminum welding, magnesium welding, and their alloys. Now, why we prefer specifically AC for aluminum welding is because its oxide cleaning nature which is available for DC electrode positive. See, DC electrode positive connection provides you a oxide cleaning which is very, very important for aluminum and magnesium alloys. In the case of alternate current, which actually consists of DC electrode positive and DC electrode negative 50-50%. So this particular feature of electrode cleaning, arc cleaning action, helps cleaning of the oxides in aluminum, and invariably aluminum is welded with alternating current. Of course, the other type of power sources which are available are the pulse current power sources or steady state current power sources. In the case of steady state current power sources, the current is constant without any change. Whereas in pulse current system, the current is pulsed between two levels. One is the peak current, the other one is a base current. This enables heat buildup to be reduced and controls the penetration also, especially for thin sheet welding. This of course reduces the speed of welding, but you are able to get a very good quality of welding. Now here in the slide, you can see the different types of currents employed in TIG welding process. The first one is a normal DC, which you expect out of any DC power supply, such as a battery or any DC power source. Now, when you are actually doing a welding, you can see the second picture, that is the direct current which is seen when welding is going on, for example, in TIG welding process. The variation you see in the DC is because of the variation in the arc length due to the manual operation, and that in the variation in the arc length induces a change in arc voltage, which in turn changes the arc current. But then still the arc is steady, the current is more or less of the same level, and because of this the penetration is also more or less constant, which is the most important requirement for welding. The second type of welding, which is the pulsed TIG welding, is actually a pulsing of the current, and you can see the current is pulsed between the peak current and the base current. The two levels are fixed based on the job thickness and the amount of heat built up that can go into this total job. We will discuss more about this in the last part of the lecture when we will talk about the creation of this particular, how the pulsed TIG welding is going to be used, how the molten pool is created with this system. Coming to the alternating current, the most common power supply which is obtained is the sinusoidal alternating current, which is coming in any power system. But in our welding, during welding you can see the alternating current is of sinusoidal nature, but there is a break in the positive and negative half cycles. This is due to the inherent nature of the welding itself, because we are using tungsten electrode on one side as one electrode and aluminum as the other part of the electrode, and these two have different thermionic emission capabilities, which induces this variation. Now this particular problem is eliminated by means of using a continuous high frequency unit during the welding of aluminum and magnesium. More advanced system which has come into the market, which is being practiced in the industry, is the square wave AC now. Now we have seen the earlier system which is sinusoidal AC, and in this case this is a square wave AC where the electrode positive and electrode negative are square in nature and they can independently control. When we say independent control, what we mean is the peak current or the current levels which are obtained in any part of the cycle can be controlled, and the width of the cycle also can be controlled. For example, the positive cycle can be made 40% of the total cycle time, or it could be made even 70% of the total cycle time. This particular variation is possible due to the advanced electronics available today, and more importantly, this enables the arc cleaning of aluminum or magnesium according to the requirement of the industry. In the case of sinusoidal AC welding, you have a system where the arc cleaning action is only 50% of the time, whereas in this square wave AC one can get even 70% of the time for oxide cleaning, and that is a very big advantage for welding of aluminum alloys. This is one of the important developments that have happened due to the development of aerospace requirements, where high strength aluminum alloys but which require higher oxide cleaning action. Now let's go into a bit more about the constant current power source. Why is a great advantage for TIG welding process? Now, as you can see in the picture, the constant current power source is having a arc nature as shown in the curve as power source characteristics, and the vertical axis is basically the voltage axis and the horizontal axis is the current axis. Now when the current is not there but the power supply is on, then the voltage which is obtained across the terminals is the open circuit voltage, and it is usually between 65 to 85 volts in the case of TIG welding process. And if you have a dead short, that is two electrodes touching each other, voltage is zero, but then the current is fully flowing, and that is called the short circuiting current, which is actually the highest current which can be obtained for that particular setting of the power source. So when a welder is doing a welding, what he does is he sets this current, let us say about 100 amperes, then a characteristic is available, is created in the system where 100 amperes is the short circuiting current, and it will start from the open circuit voltage, which is a zero current point. So like this you can vary the current according to the requirement whenever the setting is changed for 100, 150, 130, whatever requirement is there for the current. Now considering one particular characteristics, let's say that we have kept a requirement of 100 amperes as per this curve. Once the welder starts welding, the arc voltage will be coming into play, and the arc voltage is normally in the range of 10 to 12 volts according to the arc length maintained by the operator, and also depending on the shielding gas that is employed. So assuming argon is being used where the arc voltage is in the order of 10 to 12 volt is quite normal, what happens is that the arc voltage shifts according to the arc length maintained by the welder. So even if there is going to be a variation of a few volts, 1 or 2 volts, the arc current really cannot really change. As you can see in the picture, a delta V of higher value really leads to a change in delta I of very small value. So usually in the order of say plus minus 5 amperes is the norm, which happens. So the welder, when he has set 100 amperes, he may get maybe 95 amperes, or he may get about 90 amperes, the worst case, even when he changes the arc length very widely. So this enables practically a very important requirement. A welder can get a uniform heat input into the weld, and more importantly, he can get a uniform penetration, which is a very important requirement for welding quality. So even when a welder is doing in a manual way, he gets a really good quality. This type of power source is very widely used also in shielded metal arc welding, and hence it is possible for one to convert a shielded metal arc welding power source into a TIG welding power source by addition of some of the controls like gas flow control and water flow controls. Now here in the screen you are seeing a picture of standard TIG welding power source, one of the latest types, which is an inverter type. So this power source system has got simple knob control for controlling the current, and you have also in this system a pulse current control, which is a pulse on time, pulse off time, peak time, base current controls. The second important component of the TIG welding system is the torch. As we have seen earlier, the torch is an important part because it holds the tungsten electrode, which is from where the arc is initiated, and it also has got a shielding system which directly gives a shielding gas supply to the arc. It also covers the molten metal pool and tungsten electrode, which is very hot. In addition to that, it covers the hot zones of the solid base metal. Here in the screen you see a manual TIG welding torch. The manual TIG welding torch is specially designed for holding in the hand for the welder to do the welding, and it has got the tungsten electrode, which is the heart of the system, this particular torch, held in a collet. A collet is a copper or a brass component which is designed for a specific diameter of the electrode and which can be screwed to the torch body. And then surrounding this collet, you have the nozzle which is extending towards the welding area. The role of nozzle is to only provide a guidance to the shielding gas, which is to be passed on to the area of welding. Now in front of the collet you see one more component called the gas lens in the picture. The role of the gas lens is to provide a laminar flow to the gas supply which is coming out of the torch. As you increase the shielding gas quantity to have a wider area, there will be a tendency for turbulence to the system, and this is avoided by means of this gas lens. Now we will see the other important features of the torch. The torches are basically classified in two different ways. One is due to the classification based on the cooling system. That is, whether the torch is cooled by the shielding gas which is coming for the shielding purpose and also in cooling the torch body, and hence it is called the gas cooled torch, sometimes called also the air cooled torch. The second type of cooling is a water cooled torch, where water is used for cooling the torch body, and then it does not come into contact anywhere with the weld. It cools only the body, and it is also having a supply of the gas which is the shielding gas. Now as you can see in the picture, again we see the torch body, we see a collet, the collet body which is really holding the tungsten electrode, and then you have the nozzle which is directing the shielding gas towards the desired location. If you compare it to the water cooled torch, you see two more additional points. One is the water is sent into the torch body, and second one is the water is going out after cooling the torch body. The power cable is also connected in the torch water outlet line, so that the power cable is also cooled by the water. Now as you can see in this picture, the cooling types, two types of the torches are shown here, and gas cooled torch, as you can see, is usually up to 200 amperes, but special torches are available up to 350 amperes. The main feature of the gas cooled torch, or air cooled torch as it is sometimes called, is that the cooling takes place only by the shielding gas. This eliminates the requirement of water, and this is a very useful requirement when you are talking about welding in erection sites for power plants or refineries or chemical plants where water may not be available at all locations. So welders in the site prefer to use this particular torch even though they are bulkier compared to the water-cooled torch. Now, the water-cooled torch is the second type of torch, and these torches are very small in size, and since water is available in plenty, you are able to cool it very effectively. The current can go as high as 1000 amperes in some system, but usually from 250 amperes it goes up to 350 to 400 amperes without any problem at all. And water supply which is used for cooling can be from a running water like a tap which is used in the industry, or it can be even that of a closed circuit system where you have a water supply, then there is a tank, pump, radiator or chiller, and then again after cooling it again comes back to the torch body. This becomes a very important requirement for TIG welding because the heat is generated in tungsten electrode and that has to be removed. If the heat built-up is allowed, then there is a chance for the tungsten to melt, and that should be avoided at all costs. So cooling has an important role, and that can affect the welder comfort also during welding. Hence, water-cooled torch is a very preferred torch for the welder because it is small, sleek, and it's very comfortable to handle. The only issue is the water should be available at the location of welding. The second type of classification is based on the operation, that is whether it is a manual torch or machine torch. So here the functions are the same, both the torches are the same, but then the shape is slightly modified to either fit into a machine, in which case the torch is totally vertical, and if it's a manual torch there is a handle which is provided so that the welder is able to hold it comfortably. That's the only difference. Function is the same. There is a nozzle, collet body, torch body in both the cases. Now the several important points which one has to note about the torches are mentioned here. So tungsten electrode is held in the torch through a collet body. The most important aspect one has to bother about is the contact between the collet and the torch body. Now, if the contact is not sufficient or improper due to any damage in the collet walls, then the heat will not be conducted from the tungsten electrode to the body, and tungsten will be overheated. This will lead to a lot of problems in the actual operation. There is a possibility that the tungsten itself may melt and then drop into the molten pool. So to avoid it, a welder or the welding operator has to be very carefully verifying this before fitting into the torch. So the second, the water which is going into the torch also has to be of good quality without any deposits, otherwise it affects the conduction of heat from the torch body. So one has to ensure that the water is of good quality without any dirt, and it should be usually filtered before putting into the torch itself. The third important part is the ceramic nozzle which is connected to the front. The idea of the ceramic nozzle is an important factor which decides the amount of coverage which is there in the shielding. So this coverage is normally such that the coverage is 3 times the nozzle ID, and you have to choose the nozzle according to the area of coverage that is really required. The nozzle can be of different shapes. It is possible to have very narrow nozzles when one is welding in a very narrow confined space. It can be even Pyrex nozzle instead of ceramic nozzle when one wants to have a transparent view of the tungsten electrode as well as the other side of the electrode. So these are the types of nozzles, but essentially they are all ceramic in nature, highly thermal conductive but electrically non-conductive. Here in the picture you can see the role of a gas lens, which is nothing but a diffuser with a small component which is attached to the torch, which has got a lot of holes and through which the gas is emanating. As you can see in the picture, the left side picture shows the type of gas flow which occurs when there is no gas lens, and the right side shows you the gas flow when it is with a gas lens. The flow is very laminar and very, very convenient. This is an important factor when one is welding in an environment which has got a lot of wind around. So, or if you are going to weld with there you require more of amount of shielding gas. For example, in an overhead position where argon gas has to force through the air and then it has to go and cover the area, weld zone. So in such cases, the tendency for the operator is to increase the gas flow rate so that more coverage is ensured. When you increase the flow rate, what happens is that you have a problem of turbulence as you increase the flow rate. To avoid this turbulence, this gas lens, if it is put even at higher flow rates, it gives a very good laminar flow and it is very, very convenient. Tungsten electrodes have been used as the electrode for TIG welding process due to its very high melting point, which is in the order of 3450 degrees centigrade. The tungsten electrodes are available at different diameters and different lengths according to the requirements. But later developments have been made with different alloying elements, as you can see in this, to increase the current carrying capacity of the electrode and to have a very easy arc start during welding operations. In the initial stages, TIG welding was done only with pure tungsten electrode, which was used both for DC electrode negative as well as for AC welding. That means we almost welding all alloys. Now later developments came into picture. By addition of thorium oxide, it was found that one could increase the current carrying capacity of the electrode, and it was also retaining the pointed tip of the electrode throughout its operation. The biggest problem with the tungsten, pure tungsten, was that one starts with a pointed electrode, but it becomes a ball during the heating at a very high temperature, and it loses its sharpness as work is going on. Whereas in thoriated tungsten electrode, the shape is retained throughout the welding without any problem, and that helps in maintaining a steady arc, especially in the root pass welding. Now, later, people added different alloying elements. For example, first it started with 1% thorium oxide, later it went to 2% thorium oxide, then lanthanum oxide, which is around 1.5%, then they went to cerium oxide, and today it is possible for one to get special rare earth oxides also added according to the requirement, whereas as per the standards, thorium oxide, lanthanum oxide, cerium oxide, these are the oxides that are really added. Now for the case of aluminum welding and magnesium welding, where we use alternating current, these electrodes are of no use. One has to go for zirconated tungsten electrode, where 0.15 to 0.4% of zirconium oxide is added to pure tungsten, and you get a zirconated tungsten electrode, which actually effectively balls at the tip for aluminum welding, but at the same time you can have a higher current carrying capacity. Now the diameter of the electrode is chosen based on the current which is being employed for welding applications. Each electrode has got its own current carrying capacity. Accordingly, the electrode is chosen. Now, here in this slide, you can see the different types of alloying elements that is being added, and all are added almost to increase only the current carrying capacity of the electrode. And you can see at the end, there is a designation. One column number 2 gives you the designation, and then there is a tip color also given. Both are as per the American Welding Society standard. European standards have got their own color code variation, but essentially the alloying elements are the same. As I told you, you can see the first 4 types of electrodes in the screen. They are meant for DC welding, DC electrode negative welding, and used for welding of steels, copper, titanium, nickel alloys. Whereas the other 2, zirconium oxide and pure tungsten, these are employed for welding of aluminum, magnesium alloys. To give an example of the current carrying capacity of the electrodes, this particular table is provided to you, and you can see the diameter of the electrode starts from 0.5 millimeter to it goes up to 6.4 mm at various steps. And you can see the current carrying capacity also starts from 5 amperes to 1000 amperes for the 6.4 mm diameter electrode. These electrodes are available in different lengths also, starting from 25 millimeter up to 200 millimeter. There are special cases, even 300 millimeter electrodes are available, where the torches have to be very long to hold this particular electrode. But the most common is 100, 150 millimeter. 2 lengths of the electrodes are very commonly used in the industry, especially for manual welding applications. One important aspect of TIG welding is the use of a pointed electrode. The electrode, when it is bought from the manufacturer, it is flat and it is ground to a point as shown in the picture. Now the included angle is given to the electrode so that the arc will be directed towards a particular location. This is an important feature when we talk about root pass welding, where arc has to be directed to the root gap and the adjacent areas, so melting takes place only in those areas. Now, as you make a very pointed electrode, what really happens is the heat also gets concentrated in that area, and there is a chance that the electrode can melt if it is too sharp. Because of this reason, according to the diameter and the current that is employed, the angle of the electrode also is chosen. So as you can see, the included angle can be as low as 12 degrees, which is very, very sharp, as well as it can be as high as 90 degrees, which is very high. This depends on the current that is getting employed in the welding. And once you start welding, you find that the tip is retained up to some time, and then if by chance the welder touches this molten pool with the tungsten electrode, the tip is damaged. The welder really stops the welding at that point, removes the electrode from the torch, grinds it in the grinder, puts it back, and then starts welding again. And even if the welder is highly skilled and he does not touch the electrode with the base metal, the tip gets damaged after some time due to the natural wear. So maybe once in a day the welder may have to grind it before he starts welding again. The next important part of the system is the shielding gas system. The shielding gas system is basically to provide a shielding from the atmospheric oxidation, and here in TIG welding we use inert gas shielding. The inert gases are available from nature, and they start from helium, argon, krypton, neon, xenon, radon gases. Now, out of this, in welding we use only helium and argon. The helium is a gas which is obtained from the natural gas resources where the petroleum is being taken, and it is not very common in India. Whereas argon is available in atmospheric air, and these gases are collected when air is liquefied, and then it is filtered and then taken out, and in a separate cylinder it is supplied to the industries. So usually the gases are supplied in industries in cylinders, or if the volume of gas is used is very high, then they have separate huge gas containers which will pipe the gas to the desired location. Where you have multi-stations, many welders are doing welding at the same time. The type of gases that are used are argon, helium, argon plus helium mixtures according to the requirements, and sometimes argon plus hydrogen, maximum 5% also. Now these mixtures are available either mixed gases, argon plus helium of desired proportion, or argon plus hydrogen at desired proportions, or they can also be mixed with gas mixing units. Now what are the characteristics of the gases? As you can see, argon from the viewpoint of availability is very high in India compared to helium. So the most widely used gas is actually argon. Now argon has got an advantage, it's heavier than air, slightly heavier than air, and then it is very widely available all over the world. So it has got a good arc starting characteristics, which is a very great advantage for us. It has got a good cleaning action in aluminum welding because of its density compared to helium, and it gives you a very stable arc because the arc voltage is much lower compared to helium. The cone also is very focused, which is a very great advantage for doing root pass welding, and because of the lower arc voltage it is much easier to handle because heat input is much lower, and usually we require 6 to 12 liters per minute of argon for welding. Now if you see the helium is quite a rare gas to obtain in India. It's quite costly because it has to be taken from the petroleum reserves and generally not available so much. The characteristics are that helium is having a higher arc voltage. For example, for the same arc length, argon may be able to give you 10 to 12 volts. Here it will be about 20 to 24 volts. And it gives you a higher heat input, which is a good advantage when you are welding high thermal conductive materials like aluminum, copper, where your higher heat input will be a benefit. And this also leads to faster welding in other materials, which also gives you a higher, deeper penetration. But then because of the higher arc voltage requirement, you find the arc starting is also slightly more difficult, And because of its lower density, it has got less cleaning action in the case of aluminum and magnesium alloys. Because of density again, you require a higher flow rate to remove the total air which is available, and it is much costlier compared to argon. It could be as high as 5 to 6 times costlier compared to pure argon. To get a benefit of these two gases, argon plus helium, some people have used argon plus helium mixtures also, and these mixtures are very widely used in the United States. So the characteristic is, according to the mixture, the proportion of argon and helium. So you can get a much better arc starting, but at the same time you can get a much better heat available in the system. These are mainly employed in automatic welding process in some of the industries of joining stainless steel. The more common and much cheaper application is using argon plus hydrogen mixture less than 5%. Now this also gives you a higher heat input and gives you much better welding, and especially when you are welding stainless steels where hydrogen solubility is much higher, it does not have much of a problem, but at the same time you get a much better quality of welding. Another advantage of using hydrogen is its a deoxidizing nature. It reacts with any oxygen which is present in the weld area, and then that gives you a better quality, also better shielding, we can say. So this also is a very advantageous gas for practical applications, but due to the worrisome nature of hydrogen, flammable nature, people are worried about using it, but it is quite a safe gas when it is handled properly. Now if you see a gas system consists of a gas supply, which is a gas cylinder or a gas container, and then a pressure regulator, a flow meter, a connecting hose between the various components, and a back purging arrangement wherever required for welding of stainless steels, titanium and nickel alloys. Now what's a gas cylinder? A gas cylinder is normally consisting of 6 cubic meter of argon at NTP, and it is compressed to 170 kg per centimeter square and supplied to us in cylinders. Now this high pressure of the gas, when it comes out of the gas cylinder, cannot be used directly, hence it requires 2 more units for controlling the gas flow. One is a pressure regulator which reduces the pressure from 170 attar to 1.5 to 2 atmospheres, and a gas flow meter which controls the flow rate to the desired volume, which is something like 6 to 12 or 14 liters per minute. So the combination of these three will give you a proper gas flow rate as desired. Now as we use more and more of gas, the cylinder pressure also comes down, and the cylinder pressure should not be allowed to come down below that of 5 attar. So if the pressure is lower than that, there is a possibility that atmospheric air may go inside the cylinder, and then it creates a problem during the refilling stage. It contaminates the gas inside the cylinder, and in the subsequent usage you find that air also comes into the picture. So we have 3 levels of purity: pure, very pure and very high pure. So the percentage contamination or the purity levels are given as, from the case of pure gas it is 99.95, in the case of very pure gas 99.995, and in the case of very high purity it is 99.9995%. The other impurities which are possible are oxygen, hydrogen, carbon dioxide, air. These are the things which are possible to be there, but the purity is controlled very high in these cases. The cost of the gas cylinder also increases according to the purity, and based on the requirement for the product, you choose the gases. For example, for welding nuclear reactor components, one goes for very high purity or ultra high pure gases. Or when one welds ordinary carbon steel for a power plant requirement and a refinery requirement, a welding grade pure argon gas is sufficient, that is 99.95% purity is sufficient. Or when one goes for medical level tubing used in medical, biological, pharmaceutical applications, one goes for ultra high pure argon, which is 99.9995% purity. So these locations or these applications call for very high quality in welding without any oxide present. The presence of oxides on the surface is also checked in during this welding by means of just checking the color of the bead which is there. The color of the bead indicates the amount of oxidation that has taken place, and a pure or a unoxidized surface will be exactly like what was the original welding color, and slight gold color indicates slight amount of oxidation. As the oxidation increases, it goes to blue color. It can be as high as a black color, which is virtually no protection. So these are controlled by means of the purity gases during welding. Now the gas regulator, as we can see, it's what is shown in the picture is actually a two-stage regulator, where there are two stages, and in other types you have a single stage regulator, but much less used in the TIG welding process. Flow meters are meters which can control the gas flow rate, and they are available from 0 to 20 liters, 0 to 50 liters, 0 to 100 liters per minute also. The next important part is actually the filler wire. The filler wire is a very important or a unique point in this TIG welding process. In all the other arc welding processes, the filler wire is added as soon as the arc is struck, whereas in TIG welding process, filler wire is independently added. This gives an additional control for the welder. He can have only the arc without any filler wire, or he can have extra filler more than what is required as per the requirements. So this becomes a way of controlling the heat input also into the material, and also get a desired shape of the weld finally. Filler wires are generally of the same composition as that of the base material, except for special requirements maybe, especially for corrosion resistant requirements. But in all other cases, it is having the same mechanical property as well as the composition of the base metal. And filler wires are available as per the different standards, especially American standards, AWSA 5.18 for example, which is actually giving the specification for MIG filler wire, which also can be used for TIG welding processes. And the dimensions of the wires are, different diameters of the wires are available. Wires are available either in spools or straight rods. The straight rods are used only for manual welding, and the diameters start from 1.2 mm, 1.6 mm, 2 mm, 3.2 mm, 4 mm, 4.8 mm, and there are standard lengths 900 millimeter long. Now in the case of automatic welding, you have very thinner wires starting from 0.5, 0.6, 0.8, 0.9, 1.2, 1.4, 1.6 to 2.4, 2.8 mm, and one can make spools of different sizes according to the requirement. In the case of automatic orbital TIG welding, you can use a very small spool from 500 grams, and in the case of huge automatic welding stations, it can go as high as 250 kg per spool. In the case of automatic welding, the wire is being fed by a wire feeder similar to that used by other processes like MIG welding process. Only thing is the diameter of the wire is much smaller, hence the rollers have to be changed, and the feed rate is also much lower compared to that of a MIG welding process. Now in manual welding process, usual practice is to add the filler wire by hand. Now in one of the latest developments, there are mechanized wire feeders also for manual welding. Here the movement of the wire is ensured by means of a motorized system from a wire feeder which is kept away from the welder, but the position of the filler wire addition is done by means of the welder himself. Where he wants to add the filler wire, he moves the tip according to the requirement. Now the important point one has to note is the filler wire has to be added in the molten pool. That is, it has to be fed at the edge of the molten pool and not in the middle of the arc. If one adds the filler wire to the arc, what happens is the alloying element available in the arc in the filler wire evaporates, reducing the alloying element in the system. The second important point is when the filler wire is added in the welding, the welder should not remove the filler wire such that the tip is outside the shielding zone. In that case, oxidation takes place in the tip, which will add to the quality problems in the welding. So these two aspects, that is the filler wire addition into the molten pool, and it should be retained within the shielding zone throughout welding, is very, very important for any welding operation. Next important part is the accessories for the system. Now, the welding operation is initiated by means of a high frequency unit. This is an important point which we'll be discussing more in the arc initiation part. The second important system is the gas flow control system, which is a pre-gas flow and post-gas flow, that is before starting of the weld and at the end of the weld, the gas flow is continued in the tick torch to shield the molten pool. And third one is the current upslope control and current downslope control to control the amount of heat input which goes into the metal. And then water control switch for controlling the water supply to the torch in the water cool system. And then wire feeder, which is used for feeding the wire in the automatic welding or in the manual welding. In addition, standard, you have the foot switch for switching on and switching off, because the operator is actually having a filler wire in one hand and the torch in the other. He cannot use the hand for switching on and switching off, and so you have the foot switch for this welding. The last and the most important point is the safety, for which shielding is used. The shielding glasses shade number 10 or 12 to be used for welding. Regarding safety, other safety aspects, one will discuss slightly later. Now we have understood the various components of a welding system. Now let us go into the how a welding is really affected in welding. Now if you really see the welding process as such, that is process of creating a weld, it consists of three parts. One is the arc initiation, arc maintenance, and then arc termination. Let's see one by one how the arc is initiated, how it is maintained, how it is terminated. Now arc is initiated by means of two methods. Two options are available. One is a high frequency start, the other one is a touch start. Now taking touch start as the first, touch start is a very simple method where the welder touches the electrode to the base metal, thereby a shorting taking place. Because of the shorting, high current starts flowing into the circuit, and when the torch is lifted, a gap is created, and through the gap arc is started. Now this method is a very simple method employed in shielded metal arc welding, big welding, submerged arc welding, the other prominent arc welding processes. But it has got a problem of, if the welder is not very skilled, the tip of the electrode may break and then get stuck into the weld itself. The arc may be unstable in this case. To avoid all this problem, the other method, which is the high frequency method, is a more popular method. Now in this method, a high frequency unit is connected to the power source. Now the high frequency system basically gives a high voltage at a very high frequency. A high voltage is in the order of about 5000 volts, and the frequency of this particular current is about 2.5 million cycles per second, which is a very high frequency. Remember, the frequency of the current in our household and the industry is 50 cycles per second or 50 hertz, and here we are talking about 2.5 million hertz. Now what really happens in this system is, as you want to start, when you want to start the arc, you bring the electrode close to the surface without really touching it. Now you switch on the high frequency unit. The high frequency induced high voltage actually creates a spark in the gap between the electrode and the base metal without really touching. Now because of the spark which is created by the high frequency system, the zone is ionized, and immediately the current starts flowing through the ionized medium of argon in that area. Now then the high frequency unit is switched off. Now the high frequency unit, we call it, it actually gives you a very high voltage also. That is the main function. But we have the 2.5 million cycles system, so that it's a very big safety feature for the welder. When you are operating 5000 volts power supply connecting across, there is a chance the welder will receive a shock. But when you are operating it the same voltage at 2.5 megahertz, the welder does not get any shock, because because of the higher frequency, you have what is called as the skin effect. That means the current will be flowing only in the outer skin of the conductor, and even if the welder by chance touches the this power supply, the current will be going through only the outermost conductor, which is the skin of the body, and it will not have any effect. So for a safety purpose, the high frequency voltage is really used. Now this particular system is used only for starting purpose in welding of stainless steel, carbon steel, alloy steels, titanium and such alloys. When you are using alternating current, high frequency unit is continuously maintained throughout the welding, so that you do not have any problem in restart whenever the alternate cycle is going. Whenever the AC positive and negative switchover takes place in each cycle, this particular high frequency unit maintains the arc very steady without any break. So in the case of steels, it is used only for start, but when you are using alternating current, it has to be used continuously. Now one more caution for people who are really using some components like pacemakers for the heart or such electronic systems being used for the health requirements, there is a possibility this high frequency unit can create a problem by inducing a voltage in this area. Similarly, if you have very sensitive instruments or robots or any other advanced electronic system nearby, there is a possibility that this will induce counter EMF or other voltages because of the high frequency nature. One has to be very careful, especially people having a pacemaker in the heart can have some problem, and they have to be very careful with these systems. Once the arc is initiated, the tendency for the welder will be to maintain the arc steadily. Now you can see in the picture, two photographs of the torches are shown. In the left side, the torch is kept vertical, and this is how the welder will start when welding is initiated as soon as the arc is established. Now he holds the torch at a particular location without moving at the start, and slowly giving a circulation movement as the heat buildup takes place in that particular area. Once sufficient heat buildup is there, where the top surface of the material starts melting, then he inclines the torch as shown in the second picture, and then he starts adding the filler wire. Now you can see the filler wire is getting added to the edge of the molten pool as much as possible. Of course, the size of the filler rod is quite large, so you can't really 100% feed into the molten pool, but as much as possible the welder is trying to give this particular angle to this. Now the angle, as you can see in the top left picture, the angle of the electrode with the base is about 10 to 15 degrees, and the angle of the torch is 80 degrees to the base. Now we are giving this 80 degrees because the welder has to have a view of this molten pool for proper control. So this slight inclination is given according to the requirement of the welder. And the 10 degrees is given so that the electrode that is the filler wire is continuously fed into the molten pool. We keep as low an angle as possible. That is the logic on which the whole thing is working. Now in the case of automatic welding, the torch is always kept vertical, but the filler wire is added in this manner. Now you can see the next technique in TIG welding. There are two types of welding, that is TIG welding with filler wire and second without filler wire. The first without filler wire is called the autogenous welding, where the base metal itself acts as a filler and covers the area. Again, the autogenous welding, you can either have a square edge where the melting and joining takes place within that, or you can have a flared edge where you have the filler material, the base material itself is bent vertical, and then when it melts, it forms a part of the weld. In both the cases, what really the sequence of operation is shown in the picture. In the first case, what you have is you form a molten pool, keep the torch vertical. You also rotate the torch so that wider area is covered. Then you incline the torch once the sufficient molten pool is created, and then slowly start moving the torch the desired location, desired direction, but at the same time maintaining the molten pool size constant. As far as the welder is concerned, the whole welding is taking place controlled only by means of the size of the molten pool. That one has to really remember. Now if you see the second one, TIG welding with filler wire, Again, the starting is very similar to the previous one. That is, starch is vertical. Then sufficient molten pool is created by means of rotating the torch around a larger area. Once the sufficient molten pool is created, you add the filler wire according to the requirement. It is added to the molten pool at the edges, and then it is continuously taken. So this process continuously taken till the end of the weld. Now here in the slide you see sample welding parameters that are there. So any welding parameter guide should contain this information: metal thickness, what is the type of joint, whether it is a butt joint or a lap joint, corner joint or T-joint, then what is the electrode diameter that is being used, what is the filler material diameter if required, what is the current to be used. Please note there is a range of current is being mentioned according to the requirement, and what is the type of gas that one uses, either argon or helium or argon helium mixture, whatever it is, and then the gas flow rate. And this is a sample guide, and kindly remember whatever is given in the handbooks are basically indicative in nature, and one has to adjust these parameters according to the requirement of our job and according to the equipments we have. Now, but what is the real effect of the various parameters used in TIG welding? Current is obviously the most important parameter. Remember, the power which is supplied to the system is basically voltage, arc voltage into arc current. So current plays a very major role in the amount of heat input that goes into the weld pool. In addition, current also contributes to the arc force that is created, which enables a proper penetration and proper heat conduction in the base metal. As you increase the current increases the amount of heat input, it increases the arc force, hence it increases penetration. So whatever you want to have, if you want to have a higher heat input, which basically means you will be able to do a faster weld, you want a higher productivity, then you have to go for higher current. That's the first major factor one has to consider. Second one is arc voltage. Now arc voltage is something which you do not control from the power source. It is basically controlled from the arc length one maintains. And there is a very small range of arc voltage that can be really maintained to get a good weld. You cannot have a very low arc voltage which may lead to touching of the electrode with the base metal. For example, one can weld 10 to 12 volts very comfortably, but you cannot weld at 9 volts or 9.5 volts, which means actually it's a very, very low arc length, and touching of the electrode with the base metal or the liquid molten pool is very high. And beyond 12 volts or beyond 14 volts, let's say, you may not be able to maintain such a high arc length, arc itself may break. So this range of arc voltage is very, very low, but arc voltage basically only increases the bead width, and it can lead to undercut also. So it does not have such a major say in our controlling system. And welding speed is one thing which can contribute to the shape of the bead. The amount of heat input per millimeter length of the weld is contributed by this, and accordingly the amount of heating that can be taking place in the weld pool also can be controlled by the weld. But the speed actually reduces the penetration as you increase it, and as you increase the speed also the heat input for the overall system comes down. The wire feed is decided based on the volume of metal that is required to be fed and that is required to be filled, and also very importantly the amount of heat that is available in the arc. So as you reduce the wire feed, you get better penetration and flatter bead. When you have more wire feed, you have less penetration and you have convex bead. In the worst scenario, as you increase the wire feed, then what happens is you may get a lack of fusion defect in the weld. Essentially, these are the parameters which are in our control, which effectively controls the heat input. The other important process variables like the shielding gas that we are giving can affect us in the quantum of shielding. For example, if you have a higher shielding gas, it can cover a wider area, but at the same time it can create a turbulence. So one has to be very careful in using higher flow rate. If it's a lower flow rate, the shielding may be inadequate, and that also has to be considered. So an optimum biomedia has to be chosen based on experience. The other important point with reference to the shielding gas requirement is, depending on the surrounding, whether there is a lot of wind in that area, one has to decide the flow rate. So several other options like local coverage, local tent arrangements have to be made to have a less disturbance in the gas flow rate. Now, what are the steps really that are required for doing a proper TIG welding process? The first and the foremost requirement is to start with the proper welding procedure. So how is it really done is by selecting a welding procedure specification which is already qualified and recorded in the factory, in wherever we are doing. If you do not have it, it has to be prepared and qualified and tested to the satisfaction of a particular standard or a code. Once the proper WPS is selected, then we have to select the suitable power source, the filler wire, the tungsten electrode. Then what is the gas which is to be used? Usually only a limited choice is available with reference to the gas, because of the variety will not be available so much. Either it can be argon or helium or a mixture. So you connect a pressure regulator, gas flow meter to the torch, set the pressure to 1 to 2 kg per centimeter square as per the requirement, and the flow meter flow will be normally 6 to 12 liters or 14 liters per minute. Then you select a tungsten electrode, the diameter being selected based on the current which is required, and then check the tip, grind it to the required shape as per again the procedures in the company. Then you clean the joint and prepare the joint as per the requirement. When I say the joint ready for welding, what I mean is the fit up with the required root gap, required land, and required tack welding. Remember, it is essential for you to inspect the tacks before you start welding. Now, once these things are cleared, then you start the preheat of the job if it is required as per the WPS. Once a preheat is properly done, then you switch on the power source and switch on the torch. Usually every torch will have a switch in its handle or a foot switch which energizes the power source and initiates the sequence. Once the sequence is initiated, first the pre-flow gas starts. So in the case of pre-flow, the gas starts from the cylinder, passes through the various gas hoses, and it comes out of the torch, thereby removing any air which is lying there earlier. So this pre-gas flow is normally in the order of 5 to 15 seconds is given to that, so that the entire air which was there earlier is totally purged off, only argon is available and the arc is initiated. Once the pre-gas is completed, then you have the HF spark is initiated automatically. So in the case of manual welding where the sequencing controls are not there, these things are done manually. So you give a pre-gas flow based on experience, maybe about 5 to 15 seconds, and then you switch on the high frequency spark unit. So this particular high frequency spark will ionize the arc zone, and because you already have the power source switched on, that means the open circuit voltage will be available in the electrode, the arc will jump immediately and then arc will be initiated. As we discussed earlier, the arc first is initiated and kept in a particular location, heating the job. Once a sufficient molten pool is created, the torch is inclined, filler wire addition is started. Once sufficient amount of buildup is taking place, then arc is moved to the next location, and this sequence continues till the weld is really completed. Now, once the full welding is completed, then you switch off the system. So as discussed earlier, once you switch off system, you do not totally move the torch from the area, you keep the torch in the same location. Then current downslope starts. Current starts coming from the maximum value to the lower value, and then it comes to 0. That means the arc is extinguished. Then the post gas flow starts, where the gas is really coming out of the shielding and the torch for some more time, again the order of 15 to 30 seconds. This particular gas is given so that the shielding is there, still the base metal is cooled to some 300 degrees or so, where oxidation will not be coming. So the post flow is given so that the metal is protected even in the hot time, when it is very hot. After the post flow is completed, then it is possible for you to move the torch from the area. Then if the metallurgical requirements are there, post heating starts, and if there is any visual inspection required to confirm the welding is okay, all these steps are taken after this. Now here in the screen you see several options of welding. First, in the left corner you see the manual welding, but the wire is fed in a mechanized way. That is, you see the torch is moved by hand. It's a manual torch that is used, but the wire is really coming from a wire spool which is not shown in the picture. The welder only holds a nozzle through which the wire is coming out. Now you see the top right picture, it shows a typical manual welding where wire is moved by the welder by hand and the torch is also moved accordingly. Filler wire is a very long filler wire, maximum 900 mm. So the stability, the welder has to be very skilled to feed the filler wire at the correct locations. Now when you see the bottom left picture, it is an automatic linear TIG welding where welding is done by the machine and the operator only adjusts the parameters. The last one is the automatic orbital welding where the torch is moving all around for welding a tube. Here the unit is very compact. It has got a torch movement system, it has got a fire feeder system and movement system all coupled in one small box, and it moves around in a chain arrangement or a gear arrangement according to the design of the system. These things are very commonly used in automatic welding of tubes and power plants, refineries, nuclear reactor, all those components. One more type of welding is titanium welding where a chamber is used for welding. Titanium is a very reactive material, as you know, and even at 300 degrees centigrade it reacts with oxygen. So the entire welding operation is done in a small chamber where the torch is kept inside, but it is manipulated from outside and the entire chamber is filled with argon. So titanium component can never get contaminated or oxidized. These are special requirements for titanium because of the high oxidizing nature even at 350 degrees centigrade. Two more variations are shown here. Left side is a tube to tube sheet orbital welding. In this particular case, a very thin walled tube is attached to a very thick tube sheet which is a plate, and you can see that it's a plate which is shown in the vertical case and the tube is horizontally placed. So welding takes place in this case by means of the torch which moves around the corner of this interface. That you can see the welding torch and the wire feed also shown here, and all are rotating 360 degrees around the interface. The right side is a mechanized linear welding system which shows the torch and a wire feeder which is feeding the wire continuously. Now in this particular advances, I will just briefly explain what's happening in a pulse TIG welding. A pulse TIG welding is a system which uses a P current, base current, that is two levels of current for welding. This pulsing gives you a special control in the heat input that is formed. Now when the arc is initiated, the molten pool is formed to a particular size, and we saw earlier that the molten pool is maintained of the same shape by moving the torch to the next location. In cases where the uneven heating buildup is possible, like in the case of joining two materials, one is a 1 mm tube to another which is a tube sheet of 100 mm thick. The amount of heat input that we give in one side, which is a 1 mm thick tube, the heat buildup will be enormous, whereas the heat will not be sufficient at all for 100 mm thick tube sheet. In this case, the possibility of this tube getting cut is very high. So to avoid overheating, what we do is we give a very high current for a short duration. This high current which is given in the pulsed system is sufficient for heating and melting both tube, which is a 1 mm, and 100 mm tube sheet. And then after the specific duration, which is the on time, which is in the order of say 0.2 or 0.3 second, the current is brought to a lower level, that is for off time, at base current, which is very low level, to just maintain the arc, which can be in the order of 20 to 30 amperes, whereas the peak current can be as high as 150 to 200 amperes. Now when the base current is going on, the molten pool starts solidifying and it becomes a very small molten pool. So at the end of the off time, again the current is pulsed to a higher level, and during that time the torch is moved to the next spot, and then you hold the torch at the same location. Again the molten pool is created to a large size that is required. Then again it is switched off to the base current, and then the cycle continues like this, which essentially means we are producing a series of spots, molten pools, and one over the other it is overlapping, and then you get a continuous weld. This enables you to weld different thicknesses, different heat conductive materials, and even orbital welding, where you have a welding from starting from one point and then again finishing at the same point afterwards. So in all these cases, it is possible to do welding only because of pulsing, and not because if you try to do the welding with the continuous current, then the possibility of overheating is very high. So this is one of the most important advances which have been made in TIG welding process, and which is very widely practiced in the industry. So the pulsing rate can be anywhere from 1 pulse per second, which is a very low pulse rate. It can be as high as 100 pulses per second. The usual practice is from 1 pulse to 10 pulses per second, but in special application one goes even up to 50 pulses per second. Main advantages and limitations of TIG welding, the most important point which comes to our mind when we take TIG welding is the quality of welding which we get. The quality is of the highest order, and it is capable of doing all position welding, that is welding in down and position, horizontal, vertical, overhead, and also a pipe welding which will cover all 360 degrees. And the main advantage in the quality of the weld is that you have the property which is equal to that of the base material or better. And almost all industrial alloys can be welded, almost all material thickness can be welded, even starting from 0.5 millimeter stainless steel to the 500 millimeter stainless steel. High dissimilar thickness materials can be welded, as we have seen earlier, the tube to tube sheet applications, where we deal with 5 millimeter thick tube welded to 100 millimeter thick tube sheet. Coming to the limitations, two major points are observed. One is the very low productivity and the high skill requirement for the welder. These two contribute towards the higher cost and the higher investment also, which is very important, leading to the highest manufacturing cost for a component. Thank you.